Hey everybody, and welcome back to Calc 3 Online. So the plan for today is just to talk about conservative vector fields a little bit more. I want to kind of give you a test, basically another test to see if a field is conservative. There's like a pretty easy little computation we can do that, but that's kind of the main goal for today. To start off, I just want to do another one of these examples. So this is a cool one because we basically don't even need to parameterize the function, which is the part that's like really annoying and saves us a lot of time if it's conservative, right? So if we can show this field right here is conservative, then to do the line integral, we could just do the fundamental theorem of line integrals and just do f, like lowercase f, the scalar field up this point minus this one, right? And it turns out it is going to be conservative. So let's find that thing. So we basically want to know, can capital F, the field, equal the gradient of lowercase f, right? And that's what we're going to basically start with. So we want like f with respect to x to equal yz, right? We want the first component of this function to equal the first component here. So I'm going to just integrate with respect to x. So I'll get f of xyz equals, integrate that with respect to x, you get just an x on top, tacked on, and then you get like a function of, it could be y or z here, right? And then if you take f with respect to y, right, that's going to equal xz plus g with respect to y, yz, right? Now I'm going to take kind of a pause, and if we do f with respect to y, right, it should be equal to xz, right, because it should equal that part. And so this implies, right, that g with respect to y of yz, right, must equal 0, right? So g of yz, yes, not the derivative part, basically is some function of z. So it's like h of z or something like that, right? Because you could take the derivative of this and have it be just a function of z and still get 0, right? So we know that now. So now I'm actually going to go back up here, right? Back up here. And I'm going to kind of amend what I had there. So now f of xyz is equal to xyz plus h of z, right? And then we're going to take the derivative with respect to z. F with respect to z is going to be just xy plus h prime of z. And we know f with respect to z should, must, equal xy plus 2z. So h prime of z is equal to 2z. And then now I'll just take this thing, right, and take the integral with respect to z, right, to kill the derivative. So if I do that, right, I'll just get h of z equals to, 2z squared over 2. So really that's going to kill the 2 there. So it's just me z squared, and then there's like some constant, right? And so now we're finally done. So my function that I'm going to use is going to be this xyz function plus h of z, which I now know is z squared plus maybe some constant, right? And then my integral is now going to be like super easy, because I literally, to do the integral of, this right here, I can really pop in the gradient of f done with dr. Those are equal now. And it's literally just going to be f of 463 minus f of, that's a 4. That's not an f. F of 1, 0, negative 2. And so, yeah, you just literally go here and you plug in, your point, and you should be getting 81 minus 4, which is 77. And that's it. That's a good example to show kind of why this technique is so easy for conservative vector fields. So you don't even ever need to bring in parameters of t or anything. You just kind of got to figure out what this function f of xyz is, and then you figure that out, and you've got the capability to just do f of the endpoint minus f of the beginning point. This is that fundamental theorem right there. So it turns out there is a way to basically test for conservative vector fields, like if you're even going to have one. And that's kind of the main goal of this video. So last class we saw, and we just used it there, that if basically if f can equal the gradient of f, this f right here is actually, it's got a name in math and physics. It's called the potential field. But anyways, you don't really need to know that. But basically we saw if this happens, then we have a conservative field, and all the nice stuff like that last example will happen. So what that means, right, if we just unpack this, so if we let f equal the gradient of f, then we need p to equal f with respect to x, and we need q to equal f with respect to y. And we could keep going, but I'm just going to show it for 2 dimensions here. We're basically going to use that, a result from partial derivatives unit, to kind of do another test here. So we know that if we do the partial of p, right, with respect to y, then that, based on what I have right up here, right, should be f with respect to x, y, right? And we know there's this thing called the Clairos Theorem. I don't speak French. I don't know how to say it. I'm sorry. But the mixed partials, you can do them in either order, right? You can do f with respect to x, then y, or y with respect to x. Does not matter. So this should be the same as f yx, right? But that is the same as the partial of q with respect to x, right? And so it kind of implies another. So this is going to basically give us a more concrete way to kind of do this. Okay, so if the field is conservative, so if we've got capital F equaling gradient of f, then we really need to have this result with the partials. We need to have that the partial of p with respect to y should equal the partial of q with respect to x. Now what we really want, okay, is actually to flip this whole thing around. We would love it if we could do this basically as an if and only if statement. So if conservative, then this happens, and if this happens, then conservative. And sadly, that's not exactly true. The converse, which is this direction, is true in some situations, okay? And this is probably, this converse is what I feel like I tested the most often. And a lot of times it actually will work. If you check this, you'll be able to conclude this, okay, which is really what we want, because then it makes computations a lot easier. But I need to explain something called simply connected in order to go from this side to this side, okay? So that's what I'm going to do right here. So I really like this stuff because this is actually what I studied in grad school. So this all fits under the category of topology, and I actually just saw this on the internet, and this is a very, very famous mathematician. I would argue this is the smartest person on the planet right now. This guy is Terence Tao, and this is actually just true to me, so I think it was probably kind of funny. This is what I studied in grad school. I studied something called algebraic topology, and you've probably never heard of it. But if you kind of like what I'm about to talk about, you might like topology. The reason I liked it is actually because it didn't have all the annoying bookkeeping that like you get on problems like this. I was fine with this stuff, but it really isn't what I enjoy doing the most. I enjoy like a lot of big picture, weird, higher dimensional stuff that makes your brain hurt if you think about it. So in topology, there's a very important concept called simply connected. And I'm actually going to need to explain it to explain how we can go from this to this, which is going to be nice. So the real simple definition, I mean, you can read more complicated definitions, but this is the gist. Can you contract a loop on the object to a point? Okay? That's literally it. Without, like, breaking the surface and going off the surface or something like that. So, like, take this sphere. This is probably one of the easiest examples, actually. So you can imagine loops kind of around the sphere. Just, like, put a loop on, like, literally the surface. And it's almost like if you had, like, a rubber band, and you could, like, kind of roll the rubber band in closer and closer and closer, right? You could get that rubber band to basically ball up into a point without ever leaving the surface, right? You kind of like roll it down and down and shrink it down. If you think of a donut, this is actually called a torus, okay? In topology, we use those a lot. You wouldn't be able to do it because if you take this loop here, right? So it's going around the back, right? If you go through that middle hole, you're never going to be able to contract this point, or this loop, sorry, down to a point, right? You would basically be like pinching the donut, and you'd have to break the donut in half. You have to like cut it, and that's like the rules you're breaking. You can't cut the donut. You can't cut the loop and then like reattach it somewhere else. So all you can do is kind of like roll it the way I was kind of talking about it here. And actually, this loop also would not be contractible. So you could move that loop into kind of this chunk inside here, but there's sort of two fundamentally different loops on it that you couldn't contract. Now, there's a lot you could, right? Like if I took a loop right here, I could do the same thing where I could like shrink it down and down and down and down, and I can get it to a point. So there are some loops that work, but there are two fundamentally different ones that would never go down to a point. So this thing is actually not simply connected, and this one is simply connected. So I started with the 3D ones, maybe just because in my head I feel like that's what I studied the most, but you can absolutely talk about all this stuff in 2D or 1D also. So, in 2D, just objects kind of like this, like random, if you just drew like something like that and you like shaded it in, anything like that would be simply connected, okay? And as soon as you stick, if you put like one hole in that thing, it's kind of like a donut, right? It's like a flat, two-dimensional donut. And that would not be simply connected. If you put more holes in it, it's not simply connected. If you think of this whole thing as one space, then cutting it like that would make it not simply connected. Now, if you thought of them as two separate regions, then independently they're simply connected, okay? Kind of a neat little aside. There is a thing, so this is a torus. There's actually a thing in math called a 2 torus, which kind of looks like that thing. I'm trying to draw it, but you can actually have sort of three-dimensional version. Basically, imagine like fusing another donut to this donut, and you kind of have like, I don't know if you can see it, it's like one of the donuts is kind of like here, and then the other one, this is kind of where they connect, and then you have another donut down here. I'm not a good artist, but that is actually a thing. You can have like a 3 tori or a 4 tori or something like that. And the same way these are not simply connected, these three-dimensional surfaces are also not connected. And in topology, what we like to do is we basically classify different structures in space and whatnot. And so I used to work on problems where basically related to the classification of the structure of the universe. And it sounds pretty cool, and that's because it was. Or is, because people are still working on it. And basically in these problems, these holes will maybe represent certain local, oddities in space, okay, and weird punctures in space-time or something like that. And we do literally mathematics on these structures, and these holes sort of mess things up. And that's actually kind of what you're starting to see of a little bit here in why we're talking about this. So anyways, very cool stuff. Tons and tons of stuff I could say about this, but don't have enough time. So in 1D, you can do all the same stuff too. This thing right here is simple, because you could contract it and kind of roll it back down to a point. Not closed, right, because it doesn't close up. This is also simple. It is closed, okay. Same way you can kind of take that loop down to a point. You could kind of shrink this thing in, and you can get it contracted to a point. This one, kind of think of it like the way we have this one here. This is not simple. It is closed, okay, but it's not simple. And then this one is not simple and not closed, because you've got these kind of tails that sort of stick out into space, and then you've got crossing points, and so crossing points make it not simple. So hopefully that makes some sense. Really just you got to think, can I contract the loop, or it doesn't even have to be a loop, it could be just like a curve like that. Can I contract it down to a point, and we could just take this one like that, and then we could take it like that, and then we could take it like that, and then we could take it like that. We just keep doing this until we get it down to a point, basically. So that's sort of the idea with this. And then from that, we get this nice theorem. So it says that if you have a vector field on an open, simply connected region D, all right? So it's got to be one that doesn't have any holes, okay, and it's open, all right? So we're going to go through examples, and you'll kind of see what I mean by open a little bit better, I think, in higher dimensions. But so if you have that, then what you actually can just do is you can compute this derivative and this derivative, and if those are equal, then the field's going to be conservative. And a lot of things that are really nice in mathematics, a lot of applied mathematics, is actually open, simply connected regions. And so you can actually just do this quick test, and you can figure out that it's conservative, and then just sort of proceed from there. You can set up your line integrals and whatnot. So I want to go through these two kind of things and just show you how we might use them. So first one, I'm just going to determine whether this thing is conservative. So the region it's defined on is literally all of R2, right? And R2 is open. Because, basically it's just if you think of space, right, we draw arrows, right, that go forever in this direction, this direction, this direction, this direction. That thing is what it means to be open, right? If R2 didn't have arrows, right, this is why when students don't write their arrows, it actually matters a lot. Then we're talking about a finite closed box, right? That thing is not open now. It's a closed finite space. But R2 is absolutely open. There's no issues with R2 being closed or something. And R2 is simply connected because, there's nowhere in R2 that you have some weird holes or something like that, right? It's just perfectly fine. It's defined everywhere, all right? So that sets up the fact that we can use the beginning of this. That's like how this theorem works. So now we can use this test, all right? The partial of p with respect to y is just -1. And the partial of q with respect to x is 1. And then notice that 1 doesn't equal, nope, sorry, -1 doesn't equal 1. So f is not conservative. Right? So that means you shouldn't even bother trying to find the gradient of the scalar field and go through all that sort of stuff. So this is like a really quick, easy way to just get right into it and just kind of test whether or not you should even bother doing this sort of stuff, okay? So over here, if we were going to do the same kind of thing, oh, and I also wanted to say, this is actually what the vector field looks like. And you can kind of see that it's not conservative, right? Like if you imagine a loop, right? I don't see any argument where these, the connection between like these little vectors, right? And this field, it's kind of always pointing in the same direction as that path that we have right here. And so we would never have net zero, work done or something in that field. So that thing is not conservative. It's definitely giving you some sort of positive work as you go through. Over here, this thing, okay, the region that we have this vector field on is actually still R2 because, there's no undefined spots. There's, it doesn't say something else. So it's only defined on like a patch of R2 or something. This thing is perfectly well defined for all x and y. And so, this part, f is open, yep, and R2 is simply connected, yep. And so again, we can just do, partial of p with respect to y. And for that one, we get, what do we get? Just 2x, right? And then we can do partial of q with respect to x. And for that one, we also get 2x. And so, since 2x equals 2x, we see that f is conservative. All right. And again, here's a picture. This vector field, you can kind of imagine that it would kind of net you 0 on like any closed loop that you take. If you kind of look at it, you can sort of see here like a vector that moves out of the path that way. Kind of you get one up here, maybe that comes in, it's a little less, but then you got like other ones that come in here to kind of balance it out. Like you kind of get this net 0, I think you can kind of picture it as you move around that loop like that, okay? F is conservative in that one, F is not conservative in that one. All right, so one more problem that I want to do is kind of a weird problem, but I'm going to start off and I'm going to show that the partial of this thing with respect to y is the partial of this thing with respect to, partial of p with respect to y is equal to the partial of q with respect to x, okay? So, let's see, so partial of p, I'm just going to do like a chain rule, basically. Derivative of the top for p is, with respect to y, is just -1. And then times the bottom, x squared plus y squared. And then minus derivative of the bottom with respect to y is just 2y. Times the top is minus y. And then it's all over the bottom squared. And then if you look at the top, you have plus 2y squared and a minus y squared. So all of that would simplify to minus x squared plus y squared. over x squared plus y squared over 2, right? Just plus 2y squared minus 1 is 1, and then minus x squared. So that is, let's do it like this. So this one equals partial of p with respect to y. And then partial of q with respect to x. Still just going to do chain rule. I'm going to do derivative of top is 1, right, times bottom, x squared plus y squared, minus derivative of the bottom. Now we get 2x times just x over x squared plus y squared. And then now on the top, you have x squared minus 2x squared is negative x squared. And then you still have a y squared, and it's all over the bottom squared. Okay? So notice these things are equal. Okay? That's what we were asked to do in A, equal, good. Okay? So you would think, right, that if these things are equal, then the field is conservative, which would mean that it's independent of path. You know, you can do, independent of path just means like if you have 2 points, I can go this way, and I get the same answer as going that way, right? That's what independent of path means, which should happen if it's conservative, right? But that is not the case, right? And we will talk about why. So if you do this line integral, and we're going to do it over from the point 1, 0 to negative 1, 0, and curve 1 is the upper hemisphere, and curve 2 is the lower hemisphere of the circle, right? It seems like you should get the same thing, but you're not gonna. All right, so I'm gonna just do standard parametric equations for a circle. I'm gonna do x is cosine, y is sine, and we're gonna run from 0 to pi. For curve, this is curve 1, right? And then I'll do x is cosine, y is sine. And on curve 2, we would need to run from pi to 2 pi. So that one is curve 2, right? And so if I set this integral up, it would look like this. It would look like that. I also just went through and solved it because it's really quick. So you just have, you plug in your parameters, right? And then you have like r prime dt and your dot producting in there. Pretty straightforward line integral, to be honest. But it all simplifies nice. This is a 1, okay? And then if you do the integral 0 to pi, you get pi, okay? And then if for curve 2, same simplifications would all happen, except you're going to go 2 pi to pi, which is going to equal negative pi, right? So the weird thing is it looks like we are running into an issue because it should be path independent if it's conservative, right? This was equal, so why is this not happening? Well, this part, right, up here. This region where this vector field is defined, this is like super, super, super important, has a hole right at 0, okay? It is not defined at the origin because of the denominator, in the vector field. So it is basically like this kind of region right here. It is like a, open space with a hole at the origin, and you're never going to be able to, contract a loop in there down to a point because of that hole. It's kind of like the donut in 2 dimensions, right? So, yeah, that was like the weird little trick. These loops wouldn't go down to a point. So it's not defined at the origin, messes up the whole problem. So you do need those first few parts. They're super important.